Okay, I can also see. Okay, so this is the title. I will just repeat it of the presentation. It's core-based fiber array alignment for high energy efficiency fiber array to chip coupling. It's interesting that indeed it comes after these two presentations where fiber coupling definitely is a topic. A bit of an introduction about MicroAlign. For who doesn't know it, probably nobody knows it because it's a very small and early startup. MicroAlign was founded in 2021 as a spin-off of the Eindhoven University of Technology. We are located actually in the campus of the Eindhoven University of Technology in the Netherlands. And on the left here, you see a photo of the full team. Now we are basically 10 people, and we are closing our first funding round this year. So we are very excited, actually, exactly in this period. This is happening. Talking about fiber coupling and fiber array, let me express with this slide, let me explain the motivation of the work of MicroAlign, where basically we find the problem. We understand from, well, different interviews or analyzing industries discussions that, especially for, let's say, fiber array to chip coupling, there are like concerns or imperfections that could be solved in terms of best alignment, right? Because indeed there is a lot of work that it can be done, and that's be done in terms of spot size converters on chip and refractive index matching, for example, as it was mentioned by Stefan, in order to improve and optimize the coupling between the on-chip waveguide and the fiber. But there is also the need for many fibers. For example, I understand that in the case of quantum photonic computing, even 100 fibers could be connected in the future, and in the future, I mean in 1 or 2 years, to a chip in order to perform the quantum processing activity. And in case of 100 fibers, well, then the thing is that the standardly used technologies to make fiber array, which are usually based on V grooves, are, let's say, exhibit imperfections. For example, in the core eccentricity. So here I just show an example. It depends, of course, on the number of fibers. The core eccentricity can be, as a standard deviation, plus minus 0.5 micron. This can go up to 1 micron if we consider the full inaccuracy range. And basically all the effort, well, almost all the effort in optimizing on-chip structure or assembly procedure is lost in these imperfections, right? So this is the problem in terms of fiber array to chip coupling. Well, and for who this is a problem, here I'm probably also confirming this even more after the two initial talks. But here we see, for example, a schematic of a quantum photonic computer where I only focus and consider the quantum photonic part, basically the one with interferometers. And what we understand is that the inaccuracies in standard current technologies for fiber arrays don't allow, for example, the photons to go from the fiber array to the chip, and to the chip to the fiber array again with the right efficiency that actually is required. And well, basically here we see an example with 120 fibers, 10 fiber arrays, and here on the right is just an example, let's say an exercise of considering 0.4% loss per fiber, right? And here I calculated just the probability for which all the photons go from one side to the other side of the chip. And you can see what I just want to show. And the thing is clear at this point is that there is an exponential benefit or damage in having more or less photons, right? So considering the inaccuracy of the fiber arrays and considering what's the impact on this type of technology and considering what the industry needs, that's built the story to explain you actually also what we do. We thought, okay, if every fiber matter, well, every photon matters and every fiber matters, basically we thought, why don't we make some type of new generation alignment technology where actually we can align each fiber independently and at the same time, so that basically what we can prevent is the use of the problem of the individual fiber alignment, especially when many fibers have to be connected to a chip. What we see here is the front view video of a fiber, facet single mode SMF28, and in the blurry is one actuator. basically that is moving the fiber. So what we have embedded in MicroAlign is an actuator that can move at this moment up to 8 fibers. We want to scale it to many fibers, but the interesting is that each fiber can be moved with nanometer resolution and within a nice range. So what we see here on the left is basically how it works. The fiber will be pushed on an actuator. We have a comb of actuators, as we actually see also on the bottom left video. We have a combo of actuators. Each actuator has a V-groove. So basically we can employ the passive alignment advantage of the V-grooves and add actually active alignment per fiber base, right? So that basically each fiber can be optimally aligned. On the right, you see some quantitative measurement, which gives in terms of alignment range per fiber. It gives just an idea of what we can do. So each fiber can be displaced within a rhombus, which is 40 micrometers high, 40 micrometers large, wide, and each fiber can be moved with a resolution of 20 nanometers. So we have both, let's say, coarse alignment margin and high resolution possibilities. What you see here in the bottom left video, actually in this video, is one of our first videos. It's a 500 micrometers pitch fiber array. We very well know that we need to scale down the actuation range to, well, the pitch of the actuation to 127 micrometer pitch even. So the idea is that we want to use this actuator actually to make fiber arrays, and I will explain very soon how we want to do that. Here I show another video that basically it gives a 3D perspective of the actuators. On the bottom, so this is a 3D view of 2 fiber arrays which are butt coupled with each other. And on the bottom one, we see that the fibers are, it's nice that we can also see the red spots. It just gives the idea of how this should happen, right? So basically we have developed not only the actuator, but also a controller that can optimize the coupling, right? The transmission between one fiber and a chip, or one fiber to another fiber. But this gives the idea that the independent displacement is the potential, actually is our uniqueness. We can, now the fibers are manipulated one by one, but you can very well imagine that the uniqueness is that if we can manipulate all of them, we can make these fiber arrays in a practical way, right? Here I also show another video. This is how we want to use our actuation. Now you saw it from a 3D perspective, and here you see from a front view. So imagine it's a test video, so the ferrule is a bit damaged, but it gives the concept, right? Imagine that we have these ferrules with holes. The holes allow for actually allows the fiber to be manipulated within a certain range, and the concept is that we want to align the fibers thanks to a reference. It can be a chip or something else within the ferrule, and then basically fixing the fibers in positions once the alignment is achieved. This is still under development. Here I show on the right a concept 3D sketch of our fiber arrays and how the roadmap should be, and on the left actually what our steps to achieve these goals are. So our first goal is to have to realize the first 250 micrometers pitch fiber array by the end of summer, and then to scale it down with a core positioning accuracy of 0.1 micrometer, because basically this would go towards this let's say 50 millidecibel that people talk a lot about in terms of misalignment loss. And then we want to go to even 50 plus minus 50 nanometers pitch accuracy, and in 1 or 2 years the goal is to go to 127 micrometers pitch, because basically then indeed this fiber array can be used with the current designs, and you can well have many fibers close together. This was the description of the problem, the solution, the technology, where we are now, what's the concept. I think that's my explanation for the moment. In terms of the call for action, well, first of all, thanks for listening to the presentation. But basically, if you have specific requirements or challenges that you want to discuss with us, we are of course very open to discuss. If you have questions on our technology, so that you can, for example, think, okay, we can discuss if the roadmap, your roadmap fits our roadmap, and we can talk about it and see what are the specific things to be developed in specific times. We will have our first samples by end of summer. I would be very happy if some of you could try those and basically give us feedback, or if you want to cooperate in projects, because I see that there is quite a wide applications of this type of fiber arrays for quantum computing, and maybe even more for different quantum computing features, technologies, but also for different quantum technologies. And here there is, well, just information about myself. Feel free to get in touch, and that's it. Thanks for the attention.